Okay, so good morning. Let's answer your quiz on carbohydrates. So the first part was to encircle each stereocenter in each of the following monosaccharides. So let's recall. So what we mean here is carbon stereocenter. Okay. So we are referring to each of the carbon, and this will be our basis to determine which of them is considered a stereocenter. So, one way or our major criteria whether or not a certain carbon is a stereocenter is that each of its substituent groups or atoms connected to that carbon is unique. So, there are no parallel or no double bonds present for it to be considered a stereocenter. Let's start with number 1. So we have here, let's count the number of carbons. We have 1, 2, 3, 4, 5, 6. So this is a 6 carbon molecule. And we have here at the topmost, which is your aldehyde group. Okay, because of the presence of C double bond O H. So this is an aldehyde group. Okay. And this is the only one with a double bond. So if we number this carbon number 1, and this one will be carbon number 2, this is 3, 4, 5, 5, and the last would be carbon number 6. So let's individually inspect each of the carbons. We can redraw this. So starting with carbon number 1, we can redraw in this manner. So carbon number 1 would look like this. C or carbon is connected to hydrogen. Let me change the width. So we have C double bond oxygen and then hydrogen. Now this carbon is connected to another carbon which is connected to the rest of the molecule, or in other words, we can consider the other carbon as our R, or simply a substituent. Okay, now let's see whether it is stereocenter or not. Okay, whether carbon number 1 has all of its molecules unique, connected to it unique. First off, we have a double bond here, okay, which takes up 2. Okay, so it's a double bond. So this already disqualifies carbon number 1 from being a stereocenter. So it is not a stereocenter. Okay. Let's have carbon number 2. So carbon number 2, let me erase. For carbon number 2, we can redraw this as a carbon connected to an OH at the left and hydrogen at the right. This connected to the aldehyde group. Let's call it R1. And connected to carbon number 3 and the rest of the molecule. So this one, the rest, we can consider this as R2, since R1, your aldehyde group at the top, is not equal to this substituent group at the bottom. Okay, so meaning to say all are single bonds. Okay, so this means carbon number 2 is a stereocenter. So we encircle carbon number 2. Okay. For carbon number 3, so if we look at it, so still the same. So meaning to say, carbon number 3 is also a stereocenter. And likewise with carbon number 4 and carbon number 5. Okay? Because the top and the bottom substituents are unique. Now let's go to carbon number 6. Okay. Now for carbon number 6, this is bonded with a substituent group at the top. So this whole, for carbon number 6, this is your whole R1. Okay, this is your whole R1 for carbon number 6. And then it is also bonded to hydrogen. So there are 2 hydrogens. This is single bond each. So we have hydrogen, hydrogen. Or we could also say this is bonded to hydrogen, and the last would be it is bonded to OH. Okay, so this is OH. Since you have hydrogen here and here, so this disqualifies it from being a stereocenter, meaning to say carbon number 6 is not a stereocenter. Okay? Let's go to number 2. Okay. Number 2, so we can see that the first and so let's count the number of carbons. This is 1, this is 2, 3, 4. So still 6 carbons. So looking at the first and the 6th carbon, so there is a repetition. So there are 2 hydrogens bonded. So they are no longer included as a stereocenter. For carbon number 2, so the top and the bottom substituents are unique. So if we were to redraw this, carbon number 2 bonded with OH, bonded with H, and the top is R1. Okay, so this is R1, and bottom is R2, which refers to the rest of the molecules of the molecule. So meaning to say each is unique. So carbon number 1 is a carbon number 2 is a stereocenter. The same applies with carbon number 3, carbon number 4, and 5. Okay. So only 2, 3, 4, 5. The second, third, fourth, fifth carbons are considered stereocenter. Number 3. So this time we have, so instead of, so number 1 is considered an aldose, no? So number 1 is an aldohexose. This is L, aldohexose. Then number 3, so this is D, and then we have a ketone, so 1, 2, 4, so 5, ketopentose, D ketopentose. Now, for carbon number 1, let's redraw carbon number 1 because it's quite tricky, but it's not. The double bond hydrogen is already your clue whether or not it is a stereocenter. So carbon number 1 is not, okay, because of the hydrogen. So it's disqualified from being a stereocenter. For carbon number 2, you have your double bond. Okay, so you have double bond O, and then you have a substituent here. So let me just redraw it. Carbon number 2, double bond O. Then this will be your R1, which refers to this substituent, and R2, which is this one. Since you have this double bond, so this is already disqualified from being stereocenter. Okay. So carbon number 2 is not a stereocenter. For carbon number 3, so let me erase carbon number 3. So this carbon here, C3. This is bonded with hydrogen at the left and hydroxide at the right. And then the top portion is, let's say this is R1, and this is your R1. And then you have R2, which is this whole thing here at the bottom. This is your R2. So R1 is not the same as R2. We have hydrogen, hydroxide, all are unique, therefore carbon number 3 is a stereocenter. Same goes with carbon number 4. Okay. And for carbon number 5, so we have 2 hydrogens attached to carbon. So this is not a stereocenter. Number 4. So this is somewhat similar to number 2. Okay. So this is somewhat similar to number 2, where you have carbons. So let's count number of carbons. This is 1, 2. So you have 4 carbons. Okay. And it's obvious that 1 and 4 are not stereocenters, which leaves us carbon number 2 and 3. Okay. So let's have carbon number 2. It's bonded with an OH at the right, hydrogen at the left, and then, we have one substituent group at the top, and another at the bottom. So R2 is considered this whole thing here. All are unique, each bond is unique, single. So this is stereocenter. And it's somewhat similar to, okay, let's have carbon number 3. So still the same. This time, let me just erase this. For carbon number 3, the R1 and R2 scope changed. So we have, for carbon number 3, your R2 is this one, this last substituent group, while your R1 is this whole substituent group at the top. So R1 is unique from R2, therefore carbon number 3 is also a stereocenter. Okay. Last but not the least, we have number 5. So for number 5, we have here 1, 2, 3 carbons and this is at the left, so this is L. And then we have aldehyde group at the top. This is aldo triose. Okay, so redrawing number 5, this is C, double bond O, H, then we have C, and C, this is H, this is hydroxide, then we have OH, then we have H. So this is carbon 1, 2, 3. Okay, and then if we were to look at each of the carbons, okay, for number 1, obviously you have a double bond, so it's not a stereocenter. For carbon number 2, so you can redraw this as, so C2 bonded with hydroxide, hydrogen, and then we have your aldehyde group as R1 and the bottom substituent as R2. So therefore, carbon number 2 is a stereocenter. Carbon number 3, it's obvious you have 2 hydrogens. So meaning to say, it's not a stereocenter. So meaning to say, only carbon number 2 is a carbon stereocenter. Okay, so that's the answer for part 1 of your quiz. So some of you encircled all of the carbons. So that's right minus wrong. Let's proceed to part 2, which is matching type. Okay, so you are to write the capital letter of your answer, and then you are to match the corresponding items being numbered to the choices. Okay, so starting with 1 to 4, by the way, these are clustered. Okay, so we start with 1 to 4, and from A to D, you're given the visualization or somewhat diagram of each of these different complex carbohydrates. Okay. Now, we look at the structure at the right, and we can see that the branching is what distinguishes each of these diagrams. So the branching. So for number 1, glycogen, so since it is considered the most complex of all, we are left with C and D. Okay, but between C and D, so D is more spread out, so that's why the answer for number 1, glycogen, is letter D. For number 2, we have amylose. So recalling, so between amylose and amylopectin, no? So amylose is linear and amylopectin is branched. Okay, so highly branched, similar to glycogen. So since we're done with D, so amylose and amylopectin, so we are left with A, B, and C. Okay, but no, because C is the branch, so this is amylopectin. And we're left with amylose and cellulose. We can think of it as a comparison between capacity to branch and the structure, or say the nature. Okay, so since both amylose and cellulose are linear, so we go back to which component, no? Because amylose, remember, is in starch, and amylose has a more potential to bond with, or is, let's say, the pattern is, there's a tendency to change. Okay, so between amylose and cellulose and A and B, so we look at where we can find. So both are in plants also, and both are alpha and 1,4 bond in terms of glycosidic. However, we go to the subunit. Okay, so amylose is beta glucose in terms of the subunit. Okay, while alpha, this is alpha. Amylose is alpha. Meanwhile, cellulose is beta glucose in terms of subunit. Okay, so what do we mean by beta subunit? Okay, so if we were to redraw, so say for example, we have a sugar molecule here. For cellulose, there is a substituent at the top, then the next sugar would have to have the substituent at the bottom, and it goes on. Okay, so alternate. Meanwhile, for alpha glucose, so all of the substituents are at the top. So this will look like this. All substituents are at the top for amylose. Okay, and if you were to relate, so this one is beta because of the arrangement. So if alternating, there is capacity to bond with, so this substituent here can bond with, so another say sugar, another pyranose subunit. Okay, so that leaves us amylose as A and cellulose as B. Okay, so that's for items 1 to 4. 5, 6, and 7. So for EFG, so very obvious, blood sugar refers to glucose. And in terms of structure, fructose is a furanose. So you only have 5. So we have 1, 2, 3, 4, 5. And then for galactose, so we have 6. So it's pyranose. Then for 8, 9, and 10, we are to match the name of the disaccharide. So let's look at first each of the components. Okay, so for letter H, so your clue here will be the glycosidic bond. Okay, so it is down, meaning to say it is these two are actually the same. So this is glucose and this is glucose, because both are pyranoses and they have the glycosidic bond here. For letter I, you have a pyranose at the left and a furanose at the right. So obviously this is fructose. And then at the left, this is glucose. Okay. Lastly, you have glucose. Okay. Let's see. Sorry. Let's look at the OH. So let's review the OH. So glucose should be down, so it should have been here. So this one is, the one at the right is glucose. And that implies that this one here is galactose because of this OH here. This one. Okay. This is in reference to the previous one. So the one at the right is glucose, and this one is galactose. Okay, so easiest. So we have the clue here, galactose. So meaning to say, letter J is matched with lactose. Maltose, so that is letter H, where you have a glucose-glucose bond. And lastly, glucose-fructose, you have sucrose. And that completes our quiz on carbohydrates.